We're going to talk about theorems about zeros of polynomial functions. So the first one is the fundamental theorem of algebra. Every polynomial function of degree n with n greater than or equal to 1 has at least one zero in the set of complex numbers. Okay. So our first one here is it says find the polynomial function of degree 3 having zeros 1, 3i, and negative 3i. So I'm going to put this into a factored form and then I'm going to multiply it out. So I'm going to start by multiplying out my x minus 3i and x plus 3i. So what's going to happen here is I'm going to end up with x squared plus x 3i minus x 3i and then minus 9i squared. So when I multiply that out. So I'm going to simplify this a little bit. My inner piece here cancels out 3xi minus 3xi. That's going to cancel out. I squared is negative 1. So this ends up being x minus 1 times x squared plus 9. Now I'm going to multiply this out. X times x squared is x cubed. X times 9 is 9x. Negative 1 times x squared is negative x squared. And negative 1 times 9 is negative 9. I'm going to write this in standard form. And there is my polynomial with zeros of 1, 3i, and negative 3i. Okay? So non-real zeros. So if a plus bi, where b does not equal 0, is a 0. So if I have this complex number here, that is a 0. Then a minus bi is a 0. It always comes in conjugate pairs. Irrational zeros. If a plus c squared roots of b, where a, b, c are rational and b is not a perfect square, so it's not getting rid of that square root, is a 0, then a minus c squared roots of b is a 0, right? So if I have this square root, I know its conjugate is also a root. So it says I'm given 3 zeros. I want to find the other 3 zeros. So I have negative 2 plus 5i is a 0. So negative 2 minus 5i has to be a 0. Negative 2i is a 0. So positive 2i has to be 0. And 1 minus the square root of 3 is a 0. So 1 plus the square root of 3 is a 0. Okay. The rational zeros theorem. So if we have a polynomial function, p of x equals a sub n x to the nth power plus a sub n minus 1 x to the n minus 1 dot 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 a sub 1 x to the first plus a sub 0. So that's our polynomial function. We want these to all be integers. If p of q is a 0 of p of x, then p is a factor of a sub 0, and q is a factor of a sub n. Okay? So what that does is, if you remember, we have p, which is our last term. We have q, which is our lead coefficient. We're going to factor those, and then we're going to put p over q. And then now we're going to use that to find our zeros. So here we have p, which is the factors of 4. So plus or minus 1, plus or minus 2, plus or minus 4. Now I have q, which is the factors of 3. So I have plus or minus 1, plus or minus 3. And now I'm going to put all the factors of p over the factors of q. So that gives me 1 over 1, which is 1. 2 over 1 is 2. 4 over 1 is 4. And then I have 1 over 3. So plus or minus 1/3. Plus or minus 2/3, plus or minus 4/3. Okay, so it says find the zeros. So the first thing I'm going to do is I'm going to set this up for synthetic division. So notice here I don't have an x squared, so I need a placeholder there. So I have 3, negative 11, 0, 10, negative 4. And here's my pieces here. So I notice that my coefficients here do not add up to 0. Okay, so I know 1 does not work. We're trying to pare this down, hopefully get it down to a quadratic so we can factor or plug it into the quadratic formula. So I know that 1 does not work, so I'm going to go ahead and test negative 1. Okay, so hopefully negative 1 works. So here is 3. Negative 1 times 3 is negative 3. This gives me negative 14. Negative 1 times negative 14 is positive 14. This gives me 14. Negative 1 times 14 is negative 14. This is negative 4. Negative 1 times negative 4 is positive 4. That gives me 0. So negative 1 is a factor of that polynomial. Okay? Now, negative 1 could be a factor again. It could have multiplicity of more than 1. So we should probably test it again just to be on the safe side. So 3, this gives me negative 3. That gives me negative 17. This gives me positive 17, 31. Okay, we did not get it. So negative 1 does not have a multiplicity of more than that. Okay, so now I've tested 1 and negative 1. I'm going to go ahead and test. We can go ahead and test 2. We can try it. We can kind of work through these. Hopefully, we'll be able to pare this down to a quadratic. Okay, so 2 times 3 is 6. Negative 8. 2 times negative 8 is negative 16. That gives me negative 2. That gives me negative 4, which is negative 8. Close. Didn't quite get there. Make sure our math is all right because that looks really, really close. Okay, so now let's try negative 2. And we'll kind of test here. So this gives me negative 6, negative 20, 40. That's getting too big. Okay, so it looked like the 2's were, so we did 1, we did 2, we'll try 4 here. This gives me 12, negative 2, negative 8, 6, 24. So 4 did not work. If I test negative 4, negative 12, negative 26, that gets really big really quick, so it doesn't work. So now I'm into fractions. Okay, so I have the 1/3, the 2/3, the 4/3, plus or minus. So let's go ahead and test 1/3. Okay, 1/3 times 3 is 1. This gives me negative 13. This is negative 13 thirds. So that was 42. 42 minus 13 is 29 thirds. Right? 29 thirds. This gives me, 29 ninths. That's not going to go away, so I know 1/3 doesn't work. To save time, we're going to go to 2/3 and see if 2/3 works. 2/3 times 3 is 2. This gives me negative 12. 2/3 times negative 12, so is negative 8. That gives me 6. 2/3 of 6 is 4. That gives me 0. So now I know that negative 1 is a factor and 2/3 is a factor. And now we can kind of go from there. Okay? So this is A, B, C. Okay? So I can plug this in the quadratic formula. So 12 plus or minus the square root of negative 12 squared minus 4 times 3 times 6 all over 2 times 3. Okay. So this is 12 plus or minus the square root of 144 minus, 72? 12, 72 over 6. Gives me 12 plus or minus the square root of 72 over 6. So I know that the square root of 72 is equal to the square root of 36 times 2, so that's 6. So I have 12 plus or minus 6 square roots of 2 over 6, or 2 plus or minus the square root of 2. So there's my zeros, right? So I found the zeros. Here's my zeros. I have this piece. Now I can factor this out. So when I have here, this 2/3 is going to be, let me get some space here. So I already know that one. That's going to be x plus 1. Okay. So now this one actually breaks down into 3x minus 2. Okay. So there's my first piece there. And so then we're going to look at this, the second piece. When we factor this, we can plug this in as x. The book wants you to go x minus 2 plus square root of 2 and x minus 2 minus the square root of 2. And just leave it like that. They actually left this as x minus 2/3. Okay. The last thing we're going to talk about is Descartes' rule of signs. Descartes' rule of signs is basically finding the possible positive roots, the possible negative roots. So the positive roots equals the number of sign changes of f of x or an even number less, because we talked about how items come in conjugate pairs. The negative roots is equal to the number of sign changes of f of negative x or an even number less. Okay? So what's going to happen is if I want to know my positive roots here, first of all, I should know that there are 4 total roots. Whether they're real or complex, it doesn't matter. There's 4 of them, right? Because that's my degree. So I'm going to count the positive roots. So I count the sign changes. Positive to negative, that's 1. Negative to positive, 2. Positive, negative, that's 3. Positive, negative, that's 4. So this is 4. So, or I'm going to subtract by 2, 2, or 0. We have to continue to decrease that number by 2 until we get to either 0 or 1. Okay? Now I look at my negative roots. So what I'm going to do is I'm going to plug in a negative x. Well, what happens on a negative x is it just changes the sign of the odd powers. So this becomes plus 5x to the 4th plus 3x cubed plus 7x squared plus 12x plus 4. Are there any sign changes? No. So there's 0 possible negative roots. So this helps a lot because in our problem of what we just did, I wouldn't have had to even look at any of the negative roots, right? So if I found p and q here, so if I said, well, p is equal to plus or minus 1, plus or minus 2, plus or minus 4, q is equal to plus or minus 1, plus or minus 5, p over q is equal to plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 1/5, plus or minus 2/5, and plus or minus 4/5. But do I need to test -1, -2, -4? No, because I can't have any negative roots. So it already eliminated half of those possible roots. I only need to test the positive ones to see if they're zeros. Okay? So that's kind of a refresher on Descartes' rule of signs and the rational root theorem.